for the lab, I think there are several parts or several knowledge points we need to bring back home. Including the clean room, you need to know what is clean room. So the micro narrow fabrication is something different from other fabrication. So the clean room is a key point. You also need to understand the historical. As we mentioned that the cost of this historical fee covers 35% of the whole foundry of the whole fabrication. So the most expensive part, and also we have different metrology. In our lab part, you have to use different metrologies to measure the thickness and to measure the size. And you also have tried the wet etching in our lab. Right? And definitely in the end, you need to understand what is fabrication process flow. During this semester, we have discussed, we have showed so many different fabrication process flow. You need to understand the meaning. Because if you want to do the fabrication, before going to the clean room, fabrication process flow is always the first thing you need to make up. Okay, so for the clean room, I think if you go back to our previous slides, you will understand there are several key points. Right, the first is the contaminations. You need to understand the people. Okay, the users are the biggest. The people is the biggest source of the contamination, accounting for 75% of the contaminations. Right. For other things, the room structure, equipment, and sometimes the maintenance activities, right? So, and also the metallic contaminations. So I think for this we discussed about it with the history of the clean room. Okay, so when or why do we have the first clean room? Because the researchers want to get rid of the metal in the air everywhere, right? So to measure the life of this planet, right? So we need to understand have these types of contamination in our life around the air, and definitely the organic, right? So there's the photoresist during the fabrication. Sometimes it's hard to completely remove the photoresist, and with the process going, the photoresist can be the source of contamination. And also in the clean room, you need to understand the gowning process. Means you need to know how to dress up before entering the clean room. And this dress up is not to protect you, but to protect the devices from yourself. Okay, so this part you need to understand it. And also, you need to understand the flow design, right? So we have the turbulent flow, right? And also we have the laminar flow, and you need to understand the difference. That's the key. That's one of the key points in designing the clean room. Right? And also, thanks to the laminar flow, this can help us to further improve or increase the cleanliness level of the clean room. And you also can see the difference, right? I think in our NDL, the lab you use most, we are using the turbulent flow because we do not have the base flow, which means that is a single flow, so we need to make the air has the internal circle flow. While for the laminar flow, I think you have visited our phase 2, and you also have paid attention to the flow, and you can see that under the flow we have the base flow. We have another flow underneath it to deal with the air exchange, and also we have the base station or base flow to help us to provide the DI water and other required equipment to maintain or to operate the clean room. Right, you also need to understand how to do the air exchange in the clean room. Right, and this is, for example, the pressure difference that is due to the make-up air unit. You need to make the air flow from the high level cleanness to the low level cleanness. And I think our previous in-lecture quizzes has covered. Oh yes, that. Next week I'm going to give you all the in-lecture quizzes. Okay, so then you can learn from these quizzes and and be prepared for your final exam. So these are the key points of the clean room. So I think the final exam will cover these key points. So another is lithography, right? For the lithography, you need to understand the details of lithography. For example, what is mask? And I think in your lab report, most of you made a mistake about the type of mask. There are two types. One is black field, another is light field. Right? So the dark field refers to the type where the patterns are transparent, because outside the patterns, the whole mask is non-transparent. Then we call it dark field mask. For the bright field mask means that the patterns are non-transparent, while outside the pattern, the whole mask is transparent. So we call it bright type mask. Okay, so that is and also for the mask, we also discussed about the layout join, right? So and for the HMDS coating, also mentioned, and you also try this, and this can help us to improve the adhesion for the PR coating. And definitely we have other steps can guarantee or to enhance the adhesion force between the PR and the substrate. For example, the soft bake, right? The soft bake can help us to enhance adhesion and also to help us to remove the solvent and the solid the PR. Because without this step, the PR is not solid. The chemical property is unstable. We cannot move to exposure, right? That's the reason why we always have a soft bake before the exposure. You also have done 2 times optical exposure, 1 time laser exposure, right? And after exposure, you move to the development. Yeah, get the pattern. Okay, so I think this part is straightforward. We have tried 3 times. For the mask, we have different software, and this method you have tried the K-layout, which is open source, right? But typically we do not use K-layout to draw the mask. So in my group, we are using this top 3. The Cadence, well, it's a standard software for the IC layout drawing, because it also contains the library which can help you to run the simulation, which means that after drawing the integrated circuit, you can do the simulation in the Cadence. And we also have L-edit. This also can help us to deal with the large pattern, the complex pattern with millions and even billions of elements. And AutoCAD is also another variable tool, but we need to purchase a license. So that's the reason why this semester we use a K-layout, right, to try to create your own pattern. And I think all of you have bring back your own efforts, right? Okay. And in addition to, I think here is a process. You can see the whole process can be done in our campus. Prepare our TA, prepare the layout for you, right? And then send to the mask maker, which is based on the laser direct writer, comes from the Heidelberg. Then we fabricate the mask. And then you can take the mask, do the fabrication. So this, and also for the metrology, right? We tried different metrologies, right? In interferometry, right? And it can help us to measure the thickness. And we also tried the interferometry and also the profile step meter, which is shown here, right? So after the etching, when you have the step, you can use the stepper or the profile step meter to help you to see the thickness or the thickness of the step, which is more accurate compared to the first 2 optical methods. Right? You need to understand the difference among these 3 methods, right? For the first one, we need to understand the optical properties to do the fitting. Another one we can measure, right? We can measure the optical property and then to measure the thickness. And for the profile step meter, we do not need to understand what kind of material it is. We just do the measurement. It can tell us the thickness, which is more accurate compared to the previous one. But the issue is you need to etch through the material. You need to do the etching. Okay, for the lab part, we start from the silicon, right? We discussed about how to identify the silicon wafer. So go to the clean room, go to the foundry. There's a lot of wafers you need to pick up, and based on this, the major flat and the minor flat, to understand the type of the silicon wafer, especially when the size is less than 80 inch, right? With this, you can understand it. And over 6 inch, like 80 inch or 12 inch, we want to increase the yield, or we want to increase the achievable chip from the single wafer. And we can see this cut flat will affect the yield. So that's the reason why over 80 inches wafers, we are using the notch, okay, to help us to first to tell us what kind of wafer it is, and second, this notch can tell the equipment to do the micro alignment. Okay, so yeah, it's I think during the lecture we see some videos. You see the automatic transfer system, and they are using this notch to identify the orientation of the wafer. Okay, so the following part, I'm going to discuss about some key points in your lab report which you need to pay attention. Okay, which you need to pay attention. So, for example, the method to form the silicon dioxide. I think we need to do the comparison. We discussed about the thermal growing silicon dioxide, which is thermally grown from the silicon, so we need to consume the silicon, which has a good quality. We also have discussed about the CVD method, right? So you can see that for silicon dioxide, we have two methods. One is based on the high temperature and consuming the silicon. So the oxygen or H2O can react with the silicon to form the silicon dioxide, which feature the better quality compared to the CVD method, right? So CVD, I think in lecture quizzes, we also discussed about 3 types, right? And here the LPCVD, the PECVD, right? So they do not need to consume the silicon, but based on the different plasma enhanced or not, also based on the temperature. And LPCVD does not need the plasma enhanced. It can low pressure, but needs the high temperature. While PECVD is the plasma enhanced CVD, which need to be done under in the chamber with activated plasma. And the required temperature can be lower because the plasma can provide the energy for the reaction. So for the PECVD, the temperature is typically below 350 degrees C, right? So I think you can go back to the previous slides to see the details. So for the details, I think, well, here we discussed, right? We have for the thermal growing, we have 2 types. One is dry, another is wet. Actually, both of them are in the vector phase. Okay, both of them are in the gas phase. Okay, the vector phase. But for the dry, it's based on the oxygen, and for the wet oxidation, it's based on the H2O. Even both of them are in the vapor phase. Okay, and also the thickness. So typically, the thermal growing is less than 3 micrometers because when the silicon dioxide is very thick, it's hard to make these gases passing through the thick silicon dioxide to react with silicon. So that's the reason why for this method, typically thickness less than 3 micrometers. Well, to be honest, when the thickness is more than 2 micrometers, the growing rate is very, very slow because that needs significant energy to make the gas penetrate the silicon dioxide first and then to react with the silicon. Okay. And also we discussed about the method of the balance, right, between the dry oxidation and wet oxidation to achieve a good quality and fast deposition rate of the silicon chemistry. And we also discussed about the defects, right? The how fast, you always have the issue top surface, the surface is rough, and very slow, surface rough, this will be minimized. And for the lab report, we also discussed about the metal deposition technologies, right? What kind of, well, you can discuss both evaporation or sputter, but you need to understand the difference. I think our TA has just shown you the difference, right? What the difference between the evaporation and the sputter. And by the way, the equipment in the NDL, even that cannot work, that is the evaporator. Okay, I think our technician, our TA, has showed that the inside to you, right? So the inside is very simple. The bottom part that is heating and to melt the metal. So that's the reason why it's called evaporation. Okay, and we also have shown the sensor, which is here, that can help you to measure the deposition thickness by measuring the frequency variation. Okay, so you can go back to check. And, I just point out the issues in your lab report. So another issue in the lab report is, I think some of you cannot understand what is a liner marker. A liner marker are the markers you use during the alignment, right? I think our TA use the cross, okay, the left and the right to do the alignment in your second lithography. So this can help you to see the difference. And also, these are the rulers to tell the misalignment. So you did not use these rulers, okay, for the alignment. So here can help you to see the difference. And I can tell you this ruler will be covered in the final exam. So from this ruler, you need to understand the misalignment. It is a very good design. Simple but good design can tell you the difference, the lateral and the vertical directions. For example, the case 1. From the case 1, we see that the ruler aligned around at the 0, which means that it has a perfect alignment, no misalignment in 2 directions. Okay. For the case 2, let's see which line aligned. For the vertical direction, here is a line, right? So which means along the vertical direction, the alignment is good, no misalignment. While for here, we can see a line around 4, right? A line around 4, which means, and this is the left side. Okay, so which means that the pink part, okay, the pink part has a misalignment to the left with the misalignment of 4 micrometers. Okay, so you can read the misalignment directly from the ruler. That's the case 2. So for the case 3, think about it. Okay, give you half minute to think about it. We will have the single question in the final exam today. Then, like, you need to check which line has a good alignment or have the perfect overlapping, which is here, right? The 6 has a perfect alignment, which means that the misalignment here, misalignment along the vertical direction is 6. Okay, let's say this is the y direction, okay? Along the y direction is 6, misalignment is 6. Just for here is 6, okay? Then for the lateral, okay, so here, the ruler for the 2, okay? That this is the perfect alignment, no misalignment between these 2 rectangular. So which means that the lateral misalignment is 2 microns, right? So you can read the misalignment directly. And I think some of you made a mistake in your lab report. Okay. Okay, so another thing I want to point out is it's a calibration, it's a DOS calibration level. Okay, so I need to tell you why we have this. Maybe the TA did not mention. So in all the shots we have this, right? This can tell us how to optimize the DOS. So this is a pattern. This is a pattern in the mask. Okay, from here they have a good contact. Okay, so the top box and the bottom box, there's no overlapping, and it's corner to corner. We call it 0. For here, so we can see that it has the lateral separation. So the separation here is 3 micrometers. For here, you can see that the top and the bottom box, right, they have the overlap. Actually, it's not overlap. There's not corner to corner, and the shared length, shared size, okay, is 3 micrometers. So this can tell us how to optimize the DOS. So let's see the case. For example, this is a pattern in the mask, right? And then after lithography, you will get a pattern on the wafer, which means that's let's say, okay, so for here, yes, let's say the mask is it's a bright mask, okay, which means here is transparent. Sorry, this here is non-transparent, and we use the positive PR. Okay, so then after the lithography, these are the PR, pattern and PR, right? So if the pattern on the wafer, by the comparison, we know the DOS is large. So then, based on this comparison, we know that we need to reduce the strength of the DOS. That's a way for us to optimize the DOS, right? So for the next one, so for example, this is a pattern on the mask. Still the same, the bright mask with the positive PR. And if we get this, well, definitely the DOS is too large, right? And for the case, and even larger than the first one, okay? Then for the case 3, the same mask, light one with the positive PR. If we get the pattern on the wafer in this way, which means the DOS is too small. Okay, so by tracking here, by tracking with different patterns, we can understand how to decrease or increase the DOS to make sure that we can get 100% transfer the pattern from the mask to the pattern of the PR. Okay, so this is a function of these patterns.
I found it confusing of determining over and underexposed for the pattern.
Oh,
Like,
for
because
the
it is directly reverse, like for the dark field and the light field. So
I agree that it is based on the type of mask, right? It's based on the type of mask and also based on the type of PR. So positive PR and negative PR, they have different. So to discuss this, we always need to specify the type of mask and the type of PR. Over means that the DOS is large. Under means the DOS is small. It's smaller compared to the optimizer. Okay. So it is true that the same pattern under different mask and PR, you can say it is overexposing or underexposing, right? Based on the type of PR and mask. Okay, so that's for here, this is also the testing structure for you to optimize the recipe, for example, and also can tell us the minimum filter size we can achieve. Sometimes all the PR and the stepper or the the survey equipment, they have their own limitations. So we can use this testing, okay, after optimization, and we can use this testing structure to tell us the achievable minimum feature size. For example, I think in all your PR, you cannot achieve 1 micrometer feature size. Okay, I think all your wafers failed. But 2 micrometer, I think some of your wafers can achieve 2 micrometer here. The same here, right? You always can use this to do the dry run, and then you understand the limitation from the lithography. So then you can go back to change your design. Right? Because you do not want to design the devices which cannot be fabricated. Okay, so I think the last part I want to mention is the fabrication process flow. I think that next week I'm also going to discuss this a little bit. So why do we need the process flow? To help you to plan ahead and also track down the wafer movement, and to reduce the uncertainty and keep the unqualified wafers materials away from the clean. So the next slide I'm going to show you that we have different level of cleanness for different equipment, and this can help us to control the contaminations. Okay, so this is the standard. It's not standard, but the simplified fabrication process flow. Okay, so this part, the left part, it shows the cross-section view, which we have discussed many times. Right? When we discuss about the device, we always see the cross-section view to understand the fabrication process. And the right part, this table, is going to tell us the wafer cleanness. Okay, and the equipment we are going to use, the process, and the requirement. So for here, it can help us make the plan. For example, if we want to keep the good cleanness, we need to make sure that only the equipment in the clean level should be used to fabricate device. So after inserting or using the semi-clean or non-standard, which are not clean equipment to process flow, then the wafer will be contaminated and cannot be returned back to the clean level. Okay, so this part I think I'm going to discuss more next week. Okay, because I think in the final exam you will be asked to write the fabrication process flow. So you can see that step by step the equipment we are going to use, and in this equipment the recipe we are going to use. So this can help our users to follow it and to focus on the fabrication to avoid making mistakes. And so in our field, we have the foundry, right? We have the foundry. So this is a process for us to work with the foundry to get the products. So we come up with idea, which is the design. Then we do the sketch, the 3D design, to draw the mask, and then send the design to the foundry. So they do all the things, and then also help us do the device testing and send the results to us. So then we redesign the devices. So that is a typical working role in the industry. And for some industry or for some company, they have their own foundry, so they always can, do the things themselves with more details to have a quicker response. For example, you have the design, you draw the layout, and then if this is new, okay, so if this is a new product which has never been fabricated, so you need to plan the clean room process flow. You need to design the fabrication process flow to tell the clean room or to tell the user or staff in the clean room how to fabricate, and then to discuss with the technicians. So then confirm the fabrication process flow, then you can draw the mask. Because you need to, for example, you draw the layout, but you do not know which kind of PR you need to use, the positive or negative. Okay, and so after getting the mask, the process, you also need to develop the process, then execute the process, device are ready, and do the management, this kind of things. Right, so this we call customer. So do the fabrication and design ourselves. But nowadays in the industry, especially for the IC, most of the companies are using the foundry. Okay, so this is how foundry works, right? So if you want to use a foundry, there are always the rules because they only run the standard fabrication process flow. So you always need to follow the rules from the foundry. So if you want to design a new product, a totally new product, has never been shown in the market, you need to deal with the fabrication. You need to design the fabrication process flow. Okay, so nowadays many startups in Hong Kong, they are using our clean to develop their new product. Okay, I think that's all for. Okay, so here it shows the design process with the non-standard, right? Here we will show the foundry. We have the rules. We need to follow the rules and limitations from the foundry. But if we want to, get new products, we need to go through the non-standard process. It can support us the normal idea and application. Remember, in the foundry do not want to change any step for you. So you must follow the rules. There's no design flexibility. But for the go through the non-standard process, we always can have our own idea, right? New applications, and we have the back of the envelope calculation, design completely normal layouts. Right? So a lot of freedom and flexibility, but definitely we also need to handle the low success rate. Right? We also have the pros and cons, right? So the issue is hard to be transferred to the industry if there's no mature foundry you can use it. And at the beginning, you need a lot of investment and time consuming. But in the end, if we can develop a totally new product, the return is also huge. Right? Large risk, large return. Okay, so I think that's all for today's lecture. We will discuss more.